This all started, I guess, a couple years ago now. The Canadian Space Agency came to CNL and asked the question, would it be feasible for Canada to deliver a made-in-Canada nuclear reactor to provide a small amount of power to a potential base on the surface of the moon? So we've been working for a couple years to determine whether that would be feasible for us to do. And if we were to do it, what the reactor would look like and what its characteristics would be, how we would deliver it, what kind of technical risks we face, all those sorts of things. So you can imagine that if you're looking at a terrestrially based nuclear reactor, you often just add things to make the reactor, add a little bit more shielding, add a great big containment building, make your system such that it's extremely robust just by adding more materials. If you need to lift it off to space, it's not an option to make it very large and heavy. So we need to make it compact, we need to make it light. It needs to be able to function for an extended period. The specifications are for 10 years with effectively no maintenance. So it needs to be simple, very robust, and it needs to be able to withstand very high temperatures, at least as defined by the temperature of the sky that's radiating down to you, and also very low temperatures at night when the sun sets on the moon. So it's an interesting set of considerations. There are various reactor vendors that have been looking at potentially delivering solutions for space use, in particular what they're calling fission surface power, which should be differentiated from reactors that could be used for nuclear thermal propulsion or ionic propulsion or things like that. But the approach that they've taken has largely been, we have a reactor that looks like this, we're just going to modify it a little bit and put it in space, which is it's a valid place to start. But in our case, the approach is, it's more appropriate for us to take a bit of an agnostic approach to it and decide what we think would be the most optimal approach. I should also mention that this is all a potential contribution to what's called the Artemis Program, which is set up to build first sort of an analog of the International Space Station, but a lunar base, which would really serve as a bed for testing technologies, and then subsequently a base on Mars. So the idea with this fission surface power unit would be to provide a fairly modest amount of electricity, a few tens of kilowatts electric, to the colony for about a decade. And we have a range of restrictions, including 6 metric tons for the entire system, which includes not just the reactor itself, but the shielding, the thermal to electrical conversion system, the great big radiators that you need to release heat to space, and electrical cables to move the electricity to the habitation. So some interesting challenges, and it's also been very interesting to take several very large steps back from what we usually think about. And instead of saying, okay, we have can-do reactors, here's a few small changes we can make, we need to take a step back and say, well, we're not just going to look at can-do, and we're also not just going to look at specific reactors that people have designed in the past. We're going to start from first principles and decide what type of fuel makes the most sense, what type of coolant, reflectors, shielding, all these kinds of things.
Nice. That's really, really interesting. And so different from Earth, right? And you have a 1 kilometer exclusion zone for nuclear power reactors. Yeah. First question that comes to mind is when you're deploying a reactor in space, you have electricity, but you've also got many other important supplies that you may want to create, like process heat, like heat.
Yeah.
Is it, what other considerations are there? Are you looking at making hydrogen? Are you looking at oxygen production? Like what is this heat and electricity going to be used for?
Yeah, so a lot of that ultimately comes down to what's referred to in the space world as ISRU, in situ resource utilization. Ultimately, a major use of the electricity and heat, as you're mentioning, for this would be ISRU. That likely is going to follow a while after the establishment of a place for people to sleep. Their first job will be getting a place set up, habitable, and then start scaling up. And actually, when they move on to more significant ISRU, which will in particular include the extraction of water from areas of the moon or Mars where there is some water in the soil, some small ice caps in Mars and that's whatnot. So extraction of water, also cracking it into oxygen and hydrogen so you can produce your own fuel, which is a lot better than having to ship it up from Earth. But when they move to those sorts of things, they'll be looking for much larger power sources. So at that point, the idea is kind of that we'll walk before we run. Let's build a small reactor that produces a modest amount of electricity, maybe some process heat as well, as you're mentioning. But I think the secondary systems that would be required for, piping that heat around for various purposes are likely not where we want to start with this. We probably want to focus on a self-contained unit and then use the electricity for the process heat initially. But after we've done that, then we can start to dream bigger and scale up the reactor, higher power, maybe higher temperatures, and maybe the use of process heat rather than just dumping it all to space with our radiators.
Okay, nice. So one step at a time. I like that. Start small.
It's a big step.
Yeah, it's a big step. No, absolutely.
But yeah, that's the idea.
Nice. And I've heard in the past that each kilogram of mass that you take up to space, it has a certain cost associated with it, right? Tell me about that cost and tell us about the challenges there, but also how does that connect with what reactor type you're going to be choosing?
Right. So where we are right now is we're looking at the constraints that are supplied by NASA in the Artemis program and just trying to fit within those constraints and establish whether it's something that we can do reasonably with an acceptable level of technical risk and an acceptable cost, which, by the way, we'd sort of benchmark against the Canada arm, this manipulator that Canada typically supplies for big missions like this. And that's also one of the reasons why they are motivated to do this, is that because we don't have our own space infrastructure, if we want to have access for astronauts or anything like that, then we need to barter by supplying big ticket items. So this is another thing like the Canada arm. As far as the specific costs are concerned, and actually the constraints as far as the dimensions of the reactor and the mass, that does remain an area of uncertainty. You can imagine that, as with anything, if your viewers are on a nuclear channel, they're used to the idea that if you try to extrapolate across decade-type timescales, being able to predict costs very precisely is uncertain, and that's also true for space, maybe even more so than in nuclear, when you have potential disruptors like SpaceX coming into the picture and maybe being able to significantly reduce the costs. But as I mentioned, the specific dollar values of the launch are probably they're uncertain, but they're likely small in comparison with the developmental costs, development and manufacturing and whatnot. But we're still restricting ourselves to a constraint of 6 metric tons, and then there's basically the dimensions need to be such that they can fit inside the vehicle.
Nice. Give us a visual comparison, a visual kind of comparison of what does 6 metric tons look like?
Oh. Depends on how dense it is. If you have a core that is, as one of the designs that we're looking seriously at, a core that would be composed of mostly metallic uranium, that's not going to be 6 tons worth, but it's awfully dense. So a few hundred kilograms actually doesn't take up much space. But once you start considering the peripheral aspects, the shielding, your reactor core is probably going to be very, very roughly speaking, something like a garbage can size. That's the core itself. And depends on how you define with the reflector and everything, the exact dimensions, but that's a very rough approximation. This, in terms of the volume that's taken up though, especially after deployment, what you're really going to notice is the radiators, because you need to, if you imagine removing heat on Earth, You can benefit from conduction and convection off of various surfaces, and you have, like all of our can-do reactors take advantage of big bodies of water, mostly the Great Lakes, but also the Atlantic Ocean or at Point Lepreau. So we can't benefit from that in space where you're effectively in a vacuum. So you need to rely on radiation, which is very effective when it's very hot. So a very hot surface will glow and give off a lot of heat. But if you want to be able to reject that heat without having a very, very hot surface, you need a very large surface area. So what you would end up looking at is, if you stood way back, a little tiny reactor, and then a great big set of umbrellas above it, that would be the radiators.
I don't know much about space.
Yeah.
Okay, other than the fact that it's a vacuum.
I've never been there either.
Yeah, just the pictures. Tell us about what does the environment look like in terms of a vacuum compared to our air composition on Earth? What's the difference, and how that affects the reactor itself?
So there are a few factors. As I mentioned, there are a whole range of environmental effects that need to be considered for space. Of course, the atmosphere is one, and if you've got a vacuum, you can imagine that under some circumstances, you may have some concerns about leakage, because every vessel that you make, if you want it to not be at a vacuum, it now becomes a pressure vessel. So running atmospheric pressure systems is not really possible unless it's a system that can run at a true vacuum and you just evaporate things, which is typically not going to be something that you're aiming for. So that's an issue. Inside the reactor, there's an interesting set of questions, or at least between the different components of the reactor. Often we rely on the conduction and convection of the gases that are in spaces between crevices and whatnot as a means of facilitating heat conduction. So if you can imagine you have neutrons or gamma rays slowly heating up different components. If you've got gases that can convect over those components, then it will keep them cooler. In this case, you don't have any convection. So now you need to rely on direct contact conduction or else radiation, which may be less effective at low temperatures. So there are some challenges like that, but there are some good things. And that would include, for example, if you have a hot metal that combusts on contact with air as your coolant. Or if it reacts with water explosively, you don't have air or water. So now leaks of potentially pyrophoric materials are not really as much of a concern because it's coming in contact with a vacuum.
So molten salt reactors?
Maybe some molten salts might be good. I think one of the drawbacks, well, there are a few drawbacks to going in a molten salt direction, and I think one of them being that they are not necessarily as appropriate for a very compact core. Similar to, if you're looking at moderation of the neutrons and you're trying to rely on the salt for it, it's not going to moderate the neutrons over a very short distance, so you need to have a fairly dispersed core in order to have that. If you want to have a more compact core, then you need to either go with a fast spectrum reactor, which typically is not going to be a molten salt reactor, or you need to have things like hydrogen, maybe beryllium, as your moderators.
Interesting.
There are a few popular metal hydrides that are often considered. So you can actually get a lot of hydrogen stored inside a metal. Mm-hmm. And those hydrogen nuclei will effectively moderate your neutrons. But one of the drawbacks with hydrides is that they tend not to be chemically stable above maybe 700 degrees Celsius, depending on which one you're looking at. So if you want to have a very high temperature reactor, which is helpful for the radiators, so you can see how the whole system needs to be optimized together, hydrides may not be the way to go. So then there's a set of many trade-offs that need to be considered, and it's very difficult, possible, maybe impossible, to come up with a single set of rules that would indicate to you which is the optimal set of choices. Mm-hmm. But by going through an exercise like what we're doing in trying to assess the benefits and drawbacks of different approaches, you can try to avoid a situation 10 or 20 years from now where whoever will have the job that I've got right now in the future will be, every time my name is mentioned, shake his head or her head and go, boy, why did that idiot decide to go in this direction? It would have been so much better if they had just done this. So we minimize the probability of that happening by kind of doing our homework first.
Absolutely. But one question I have, a bit of out-of-box thinking here, but you're looking at the tokamaks and various fusion technologies. And a lot of them have vacuum vessels, right? And so the advantage of space, I would say, is like the whole space is a vacuum, right? Has your team explored that option? So
in the very long term, it's possible that fusion, I mean, we know that fusion works in space. It's bright outside right now, so we know that it's still working. But it's not something that we want to rely on in the near term. If we can make fusion work in a net positive fashion on Earth, then we can consider deploying it. But having the first functioning tokamak in space seems like you're trying to solve multiple problems at the same time. But I agree with you. It can be potentially beneficial to have an infinitely sized vacuum chamber around your reactor.
Right now, space reactors, like a lot of spacecraft and a lot of equipment on space is powered through space reactors, right? That use plutonium as a power source.
So I'll just be a little bit particular about the semantics here. Those aren't space reactors. They are like plutonium-238. It's undergoing decay. So there's no sustained fission reaction occurring, but it's decaying and giving off alpha particles, which produces heat. So you need a reactor to produce the plutonium, but there's no fission reaction going on. And those are, if we had a very large supply of the alpha emitters that you use for those types of applications, then boy, that would be a very compelling case, at least for small scale. It'd be very difficult to scale it up to many megawatts of electricity. But for small scale, if we had a lot of plutonium around in the right isotope of it, then it would be compelling for small scale power and heat production. But I wouldn't quite call it a reactor. And one of the big challenges then, as I mentioned, would be scalability.
For sure. And I guess for those who are listening in with a non-nuclear background, I would say the difference between those sources and the reactor that you're envisioning is kind of like the decay heat from the core of the Earth compared to nuclear power reactors, which are actually fissioning and creating the electricity.
Exactly, yeah. And you can, one of the challenges with the decay heat, I don't know if I should say challenge exactly, but you can't directly control its power level. It's going to just, well, if you've got a radioisotope generator, you're going to be producing a given amount of heat that just very, very slowly decays over time. If you have a reactor, you can turn it off and on. When you turn it off, it doesn't immediately go to zero. There's a decay there as well, but it's a lot easier to ramp up and down if required for your application.
Definitely. This has been a really cool conversation. This is my first time talking about nuclear space reactors and learning about them. And I think those in the nuclear world, this is definitely a really cool topic. So thank you so much, Justin. Really appreciate your time.
Thank you.
Appreciate this conversation.
Yeah.